time for another DraftScience video presentation. Alright, so we're probably going to talk about friction and free energy and the car thing, and car that goes faster than the wind, stuff like that. Anyway, so Pyrrho made a video that was kind of useless, of course, but whatever. Whatever. So there's one point where he's doing his little pretend to do some math thing, and I just find it to be rubbish. So I'll just point out the rubbishness of it, and then we'll get to the car thing. So I guess I should say, I mean, he made the video. He says things that aren't very smart, but I've said some things that aren't very smart on the subject also, in the sense that you're guessing at possible ways that, what's pushing what. Does the wheel cause the propeller to turn, or is the propeller causing the wheels to turn, and all of that kind of stuff. And all the explanations are still just a little underdone. You can't just say leverage, because levers don't give you back more energy. They give you back the same energy, just over a different amount of time. So it doesn't really explain it. You need more than that.
Equals the force times velocity. See how that works? That's because energy equals force times distance, right?
So this whole distance thing and time thing is that's just units. So time is just a unit. It's a unit of time. It could be a second, it could be a minute, it could be an hour. It's just a unit. So it's telling you how much the force applies, how much energy it applies per a unit of time, which doesn't really say anything about the total force. So it doesn't really say anything about what the force is when you put it into units. It doesn't tell you the total. It doesn't tell you how many units there were or any of that kind of stuff. So it's not very useful as a way of arranging the variables. It's deceptive even.
And then energy equals force over time, which means it equals force times distance over time, and velocity equals this is the unit analysis approach. Unit analysis approach.
So all of that, so is what he's saying doesn't even match what he's writing. So that doesn't help much. Velocity equals distance over time. Well, no, velocity you can measure directly, okay, and again, it's just units of time. So I can go back to F equals ma, and I can point out that Newton's original formula was F equals momentum divided by a unit of time, and the unit of time can be anything. Could have been seconds, could have been minutes, could have been hours, or it could be the total amount of time, which would make the unit of time 1, which would mean that force equals momentum, which is kind of obvious, in my opinion. The force that acts on something changes its momentum. It changes its momentum by a certain amount of momentum. Okay, so the force is momentum. And it makes sense because everything that imposes a force has what's called momentum. Photons have momentum. All of these things, electrons have momentum. Everything that causes something to move has momentum. So everything we call a force is really just a blob of momentum that's going to be imposed on something. And we're just saying, well, it's not a blob like somebody pushing. It's the wind, or it's radiation, or some other form of a pusher that we can't see. And so, but we do know the pusher has momentum.
You ignore.
And it's going to exchange it.
All that stuff I was saying earlier about limits. But see, this, boom, d over t equals velocity. So that means...
that means, so he's writing joules, newtons, and watts, and he's saying something completely different, which I don't know, who knows. So that's the part I wanted to get to. Joules plus newtons plus watts. I don't know exactly why he's writing it that way, but he's going to make this basic statement that, again, I totally disagree with, and I don't think he has any justification in saying what he says.
Means this equals force times velocity, and that's why joules and newtons are not the same.
Well, obviously they're different words. So we know that a newton is 100 grams. How much does it weigh? It's a pressure. It's a weight. A newton is a weight. It's the weight of 100 grams in natural Earth gravity, on the surface gravity. It's a weight. It's a pressure that gets applied because the newtons are in gravity. Okay, the weight, the mass is in gravity. And then we know a joule is just dropping that newton 1 meter in gravity. It's a weight. When the 100 grams hits the ground, it's going to weigh a certain amount. There's no doubt about it. They haven't, and they will convert a joule into a foot-pound, right? Which is kind of funny because now we have a pound falling 1 foot. Okay, so what do we think the significance of a pound falling 1 foot is? Well, the significance is it hits the ground with a certain amount of momentum, weight. And weight is critical to what momentum is. Momentum is weight. It's all weight. A newton is weight. A joule is weight. A watt is weight. It's a force, a pressure in the wire.
Does not equal, watts. Does not equal weight.
So joules completely equal watts, okay? And so all you do is you say joules we're going to use the unit of time. See, they always force a unit of time on things. And so it'll be seconds. So for a joule, it's seconds. And for a watt, it can be seconds. And so then 1 joule second equals 1 watt second. Those are equivalencies.
Does not equal, certainly does not equal force, because these are all related.
Yeah, certainly doesn't equal force, he says. Okay, so he just says it. I would say it's kind of, in my opinion, obvious that it does. So, I'll draw that part real quick, just because it's a real important place where, like in the 1800s, they fiddled with the math to justify the mv squared crap, and they came up with this perversion of Newton's physics. And they'll claim it's Newtonian when it's clearly not. So Newton clearly said force equals the change, okay, in your momentum. All right, so this is just your m times your v. So the change in either your mass or your velocity. Now, obviously, in all these situations, your mass isn't changing. Your velocity is the only thing that can change. So it's really a change in your velocity, okay, and then it's over a unit of time. What's the unit of time? So you can see if I say, okay, the whole experiment, the whole transfer between, this thing transferred its energy to this thing. So this thing had momentum, and then it gave the momentum to this, and now it doesn't have it. It has 0 momentum. Okay, so it gave all its momentum to this. That took a certain amount of time. Now I could say, okay, it take 2 seconds. I could put 2 seconds in here, and then I would have an answer per second, because I would be dividing by the number of seconds. It was 2 seconds, so I'll find out how much happens in 1 second. And that'll tell me per second how much force was being transferred. Per second, there was only half an arrow in the first second, and then half an arrow in the second second. And that's how the whole arrow got transferred, because it took 2 seconds. All right? So what if I just make the unit of time 2 seconds? The time it takes for the whole experiment to happen. So I make the unit of time 2 seconds. So now time isn't 2, it's 1 unit. 1 unit is 2 seconds long, so I'm dividing by 1. So clearly I can just erase this part. I don't need the stupid fraction anymore. And what do I have? I have force equals a change in your velocity. I mean, it's a change in your momentum, but again, we're saying these things are things that aren't going to change mass. So it's just force is your velocity, and your velocity means something based on how much mass has the velocity, kind of obviously. So, the more mass you have, they don't equal each other. The more mass you have, the velocity means more. Well, okay, it's not in the picture, right? But anyway, you get the picture. So the change in your momentum is clearly what the force equals. If you just say, we're going to say, what is the whole experiment? The whole transfer. Let's just concern ourselves when this thing hits this thing, and then this thing is now left, the experiment's over. So when this thing and this thing are no longer in contact, the experiment's over, and we know the outcome, and this will predict the outcome. The force you applied will be exactly the change in the momentum. This will change momentum completely equal to what this had as momentum. that's what's going to happen, and that's what it predicts, and that's Newton's physics. So Newton's physics clearly says that force equals momentum. Force is a momentum. It will be transferred to something, and that's all you're doing, is converting the force from one form of momentum, one kind of thing moving with mass and velocity, to another thing moving with mass and velocity. And that's all there is. So the force, and this only counts the force you actually use, right? So in this equation, we're talking about wind. And so there's a whole bunch of wind, okay, little wind elements. And now the question is going to be, how many of those wind elements going 10 miles an hour can you access? And obviously by tacking, sailing at the angles, you can access more of the wind because you keep moving to a new wind vector. You keep going to new wind, and you don't have to sit where your stalled wind is. So installed is kind of important to airplanes and aerodynamics, and so all of this fits together in this moving car thing. But anyway, all right. So sorry, lack of air for some reason. So let me just finish the statement here.
But some are, divided by time. Some are, could be times time or times distance or.
So it's just this vague blah 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 blah. Okay, it's not saying anything. Why is time in the equations? And time is usually in the equation to give you a per second understanding of the rate at which the force is being applied. But in most collision cases, who cares about the rate? You don't care about the rate of energy transfer when you crash into another car. Who cares about the rate at which you transferred your energy? You care about what's the total amount of energy I'm going to have to absorb. Now, sometimes rates do matter in terms of g forces and that kind of stuff. How fast you have to absorb the energy does matter to us. So if we have more time to absorb it, we have, like a bullet example. A bullet's going slower, so we have more time to absorb the energy. It can do less damage.
Times distance over time, or these are all make different units because of those slight but significant differences. So let's just erase that and continue.
On the wheels.
Now, see, I'm sure he said it here. He said, but force is never weight. So let me play it again because he said it.
Force over time, which means it equals force times distance over time, and velocity equals this is the unit analysis approach. Unit analysis approach. So you ignore all that stuff I was saying earlier about limits. But see, this, boom, d over t equals velocity. So that means this equals force times velocity. And that's why, joules and newtons are not the same, does not equal, watts, does not equal weight, does not equal, certainly does not equal force, because these are all...
Okay, so it certainly doesn't equal force, but he says it doesn't equal weight. When, of course, a newton is weight, and a joule is, again, just a weight, but you've increased it by giving the weight momentum. More momentum. It already has momentum just sitting there. Everything in gravity has momentum, but you have to put something in the way to stop it from having its, from actualizing its movement. So it's always being pushed by a force, and it converts it into internal momentum. It is moving. Parts of it are moving. You're sitting here in gravity right now. Parts of you are moving that way. And the ground is pushing back, and you can feel it. And it's pushing parts of you back this way. And you end up with the same number of parts going down as you have going up at any one moment. But parts of you are clearly moving. And that has to do with the whole time warping bullshit of Einstein's relativity, where you're changing the radioactive decay of isotopes based on their position in gravity, because on the surface of Earth the isotope is moving a lot more because of gravity and being pushed back than it's being affected up in space. In space it's not bouncing as much because it's in much weaker gravity. Alright, so I play that part. Maybe I'll play the other part where he does his little whatever, why he can't argue these arguments with the actual people making arguments. Yeah, so maybe we'll find that little clip and throw that in, and then we'll get to more of the basic theory of this wind car thing. All right, well, it's probably worth throwing this bit in. Just because it's, again, it just illustrates the glibness of Pyrrho.
I disembarked from the dock and was like, this is cool. All right, well, that's the entirety of this stream. Don't forget the public service announcement about lucidity, helping people out, like Hythloday would have wanted me to.
Okay, so he brought up Hythloday, and Hythloday hated this attitude of Pyrrho's, that I'm just here for the entertainment or whatever, helping people out thing. They're arguments about facts and what reality is. We're arguing, we're disagreeing, we perceive different mechanisms and models, and we perceive the evidence to fit these models differently, and that needs to be parsed, and you need to take that apart and find out where we're going wrong. There's two people in the jury, one saying guilty, one saying innocent. This isn't like fun and games or something. It's a little bit serious. The fate of the human race depends on getting right answers to questions. Getting wrong answers isn't any good. Hythloday had those kinds of opinions about arguing philosophy or physics and science, and arguing in general, is that the point of it is to find the errors and to correct them, to find if there's some information that we can glean that can prove one theory better than the other theory. It isn't just some poofy bullshit that you're engaged in. So you're sort of like, playing with Hythloday's corpse and saying you're honoring it by saying something that Hythloday wouldn't like you saying. Hythloday wouldn't like your lucidity argument. Okay, they were just here to be playing some, I heard your argument, I just didn't pay any attention. I'm completely lucid, I'm completely paying attention, but I'm really not thinking about it, and I really don't care about the facts. No, that's not, you're not honoring Hythloday's memory by playing that game.
I cannot change my focus from becoming more and more lucid to proving I'm correct. However, since
so why? But regardless, so you say you can't do it. Well, I mean, I think you have to do it if you're going to argue with rational people, because rational people recognize that logic is important and facts are important, and the fact is that if you keep allowing people to say I'm a very good driver, when they're not a very good driver, then you're in big trouble.
More lucid does make me more correct. I can point out more.
So more lucid makes him more correct, which again is just, so he's just playing with vocabulary here, circular vocabulary, like the word lucid has any real meaning anyway. No, it doesn't. It's not very useful.
About being correct. So I will try to do that just for all of you and everything, and the good of the show, naturally. All right. Cheers to everybody. Have a great weekend. I hope the weather is great and it's a good summertime situation. Oh, geez, I was going to record this locally as well. So
well, that's all bullshit. All right, I'll find the part where he does a little rag, and I'll be back. Nah, should be back. So yeah, it was right here at the end.
Daniel Super Chat project. And then Manatee Johnson, you should debate in Manhattan again. That's how that's pronounced. The Betel is silent. And, yeah, well, I would, but he just has to basically submit to his own rules of civil discourse.
So again, just absolute nonsense that any of my videos are, generally speaking, not civil discourse. So, I mean, I make physics videos. You can make arguments to the physics in the videos. And that's not really hard to do at all. Like your video, I could play just clips of your video, and I don't need to get personal or any of that kind of crap, and just make arguments about what you said in the video. But instead, you had to make it personal. Instead you had to say that somehow I don't understand what civil is, when, of course, it's exactly the opposite problem. You don't understand what civil is. I mean, so he says the magic words here.
regardless of who started it.
Regardless of who started it. So again, it doesn't make any sense, right? So he says he's lucid, but he thinks it doesn't matter who starts a war, for example, or something. Well, yeah, it sort of does matter who, provokes the unacceptable, who does the first unacceptable act, and then I'm supposed to accept it. No, I'm supposed to not accept the unacceptable. That would be my logical obligation, is to say that's not acceptable, so I'm not going to accept it. Here's some of that back. I mean, how do you teach your dog? I mean, you have to have reward and punishment. Treat me badly, I'll treat you badly. Maybe you'll learn from the experience. I mean, if you're lucid enough, you should be able to learn from the experience.
That can happen? You really think that's going to happen?
Yeah, you really think it's going to happen? I'll just imaginarily fake a perception of somebody else's videos. Like I said, I've made 15,000, maybe 20,000 videos the last 15 years. 99.999% of the content is this. Just, trying to have a rational conversation about what reality is. So this argument that somehow I'm the one that gets too personal, I mean, bullshit.
I don't think that's going to happen. All right. I'll debate anybody else, though. But we have to...
So anybody else want to just paraphrase my arguments? Yeah, I appreciate it, I guess. Right? That's what it has to be. I'll wear a little bag over my head and pretend to be somebody else. I mean, the arguments are the arguments. If you could just stay on the subject, then there wouldn't be a problem. But you can't do that. And you're the one who can't do it. Anyway... All right, so the interesting thing is this little clip of when they're doing the experiment in the, right in here. Okay, so, and I pointed out, I mean, this is sort of an important part of, where these videos sort of fail. People do science videos and they just sort of fail.
And then win.
Okay, that's not the one I want. A little further down here where she's doing a little... All right, so they make the model. They create a synthetic circumstance. It really isn't the same circumstance, of course, but it'd be better to do it in a wind tunnel, something where you could duplicate wind and then start analyzing what matters and what doesn't matter. I'm going to need to do some erasing, so I'll pause and be back. Alright, I'm back. So, Pyrrho sort of fell for the 3D printing kind of thing. Like, oh, that's so cool. When, it's a really easy cart to understand. It's just a gear, okay? One little gear, and a bunch of tubing and a propeller and wheels. I mean, it's really just nothing to it. And, whatever. Won't argue the point. Obviously, mass-produced, it would be, $2.48 object. Anyway, so what do I say? Okay, so here's the cart. Okay, a little car. And what did they, why? They obviously didn't start the car on a conveyor belt going from 0. They didn't go like, let's try it at 2 miles an hour. Let's try it at 5. Let's try it at 10. That kind of thing. They just went to 10 because they knew that's probably the best speed to do it at, for it to work. So again, it's conditioning experiments to the circumstance. Now the idea would be is to have 2 springs tied to the cart, right? One in the front, one in the back. Okay, so and I have to have this further over, or you can't see the whole board, right? Yeah. Anyway, so the car is on this conveyor belt, all right, with this little propeller. What the hell? The idea would be is that if they just tied it, okay, so you put a little spring here and you tie it in the back with a little spring, and now you can do the conveyor belt at any speed and you can see what tension there is. So you're going to see that when you're started up, there's going to be obviously a force that's just going to push the car that way and you're not going to get anywhere. So until this car has momentum, it has nothing. So you have to get the wheels rolling. All right, you have to overcome the fact that you have to have, it has to be moving and the friction has to be reduced before any of these effects take place. So these are So his car, I was, the person who said that Veritasium was pushed, it wasn't. So apparently the propeller car just starts in a dead wind. So you just have a wind of 10 miles an hour, and you put your car in there, and the car gets pushed, even though it doesn't look like it could possibly catch much wind. I mean, it's not much to it. And, of course, the propeller is going to turn the wrong way as the wheels are turning. So it really doesn't seem intuitively that this thing would move anywhere in a 10-mile-an-hour wind, but apparently it does. I mean, I'm surprised it can move a 150-pound person plus the weight of the car with so little profile. I mean, it doesn't have a sail on it, so you're almost saying, how does it get going? But anyway, apparently it does. They didn't show that part, but apparently it does, because they didn't say anything about pushing it. But anyway, so we know that on the conveyor belt, though, they're relying on momentum. She holds the car firmly, in one place to get everything rolling. So momentum has something to do with being able to do this. But then I brought up the fact that you could make you could have a water wheel. Okay, so you have a stream of water. You put your water wheel in it. Okay, and it's connected to a turbine. And so what's happening when you're doing that? Because you're creating energy, electricity, lots of it. You could be pumping it into a battery somewhere. And storing it as you're collecting it. And what's really happening is say if I did have a turbine in here, and I don't let the turbine turn, that is, I lock it, well, then the building feels more stress, right? So the force then ends up going into the ground. So I shouldn't have the ground into the water. The force ends up going into the ground. So the water hitting the wheel ends up going through the bearing, going into the turbine, going into the mounting, into the ground. And so when I release it and I let the turbine turn, what am I doing? I'm allowing some percentage of the force that would have gone into the ground is now going to go into the battery or into whatever the storage device is. So if I convert the storage device into not a storage device, but instead I take the electricity and put it into wheels on the turbine factory, theoretically I could take all the energy I'm getting from the turbine, put it into the wheels would go against the current, right? I can have them go either way. Now if I go with the stream, obviously then I'm not going to gain any extra energy because my wheel's not going to turn as fast if I go with the stream. I'm going to get less energy in my wheel, so I have to go against the stream to get more energy into the turbine and to make the wheels go faster. So I'm going to go faster upstream than downstream. So right there you're intuitively, wow, that's messed up. And then you have the other fact that as I'm going against the energy, I'm not just not losing energy, I'm actually gaining energy because now the wheel is going to spin faster because I'm moving into the force, the water. So I'm gaining even more energy. So I have more speed going upstream than I have going downstream, which that doesn't strike me as, well, that's the way physics works. But yeah, I mean, obviously it's the way it works, but we have to understand what's the real difference. And the difference is just that the energy, we don't realize that you can play with the friction part. Friction is a loss of energy in any circumstance. And so if you can reduce the friction, that is, you can take the energy in some other form, the rotation of the generator, instead of pumping it into the ground, so you're really taking that part of the energy, and the more you take, the more you're getting. So it's like an airplane gets more and more stable the faster it's going through the air. So now the plane doesn't want to spin because the motor's spinning, right? The motor's spinning and spinning with the propeller, but that's once it's putting an equal force on the plane. But the plane can more than overcome that the faster it's going because of the amount of pressure it's creating to balance it is so much higher than the torque of the propeller blade. Yeah, well, I don't, well, that's what this bottom line, what this all gets into. So let me find the eraser again, and we'll go on to the next part. All right, back. I guess I could just make this bigger. Probably be a better idea. So anyway, all right. So the wind car thing. So I made the argument that the whole sailing tacking thing. So you know that you can tack across a wind. So if I have a wind of 10, and I sail across the wind. We've got to fix this chalk dispenser. All right, if I sail across the wind, I can gain more than 10 miles an hour of velocity, okay, because I've added another vector. What I would argue that's really happening is you're refreshing. So you're hitting new wind here, then you move to a new spot and you're hitting new wind here, and you're hitting new wind here, and you're not stuck with the dead wind on your sail. So like if you're regular sailing, the problem is the wind comes in and you end up with a bunch of dead wind inside your sail. It's not doing you any good. So it's almost like an extra mass that you're dragging along. The wind you stopped, let's say they were atoms and they hit your sail and they transfer their energy. They're now dead atoms. And so you're collecting a bunch of dead atoms, in your sail, which is essentially just weight, and it slows you down. Kind of, it's probably not exactly accurate, but you get the idea. So if your sail can keep cleaning the dead ones out, okay, because it's not some angle or something, and you keep refreshing the wind you're hitting, then you can gain more than the 10 miles, an hour of the wind. I should be using knots, I guess, but whatever. And so the point with the propeller blade on the car, I guess my argument would be, is what's a factor in all of this is you could sort of see a propeller as a sail, but it's a very small sail, okay. But as soon as you start rotating it, right, you're making it into a really big sail, because the faster you rotate it, the more space it starts filling, right? It even visually looks that way, right? It looks like the blade just becomes one continuous thing. So it's almost like it's a complete sail of that size. And so the faster you make it go, the more opaque it's getting, so to speak. The more opaque to the wind. And the catch is that it's catching the wind the same way the tacking, the sailboat going across the wind is doing. It's doing the same thing the across the wind thing is doing, because the blade is pitched. So it's going across it. Now the fact is this isn't going, it's not tacking with the wind, it's tacking against the wind. Okay, so that makes it a little more complicated. But then you just get to the lift argument of a wing, and the fact that you're just creating more pressure on one side, you're pushing air this way, and to push air this way, you're pulling air out of this side. So you're making this low pressure and you're making this high pressure, and now things will just move based on which side of the pressure gradient they're on. So obviously by turning the propeller into a fan, blowing against the wind, right? So you're blowing against the 10 mile an hour wind, and the faster you spin this rotor, the faster you're pushing against the 10 mile an hour wind. But then you're still back to the how did they ever get this thing started question, because it doesn't seem at all intuitive that you'd even be able to get it to start moving. And that's why I brought up the fact that they should have taken the experiment on the treadmill that one step further, just to show when this spring starts feeling, so the car is here and you have a spring here and a spring here, so you start moving the treadmill. In the beginning, this spring is going to be stretched, right? But there's going to be some point at some velocity where this spring will start stretching, and this one will be the one that will come, will go back to normal. So this one will get relaxed, there'll be no pressure on it, and this one will start having pressure put on it. And that would have been an interesting way to do the experiment, so you could actually see how it does this transition, because theoretically it should do it at any speed. So if we can keep the cart on the treadmill, it should be able to do it at 5 miles an hour. There should be a point where even at 5 miles an hour, the cart starts moving this way. Anyway, so that would have been helpful anyway in understanding. So the point is that so what you're doing is you're taking moments of snapshots of the wind with a propeller, and by moving out of the place where you've killed the pressure to the place where there's still pressure, you keep evading the dead pressure you created by the transfer. So you keep leaving the dead air behind you and getting to new air, new air, new air, new air, new air. So the faster you can move the propeller, the more new air you're hitting. Now eventually you're going to make this so opaque that it's like a sail, like it's complete. Now you're taking advantage of all you can take advantage of, because you've gotten all the new you can ever get. Your propeller's going fast enough where you actually start catching up to your dead air, when you hit your dead air again. So you get the propeller going fast enough, you'll hit the dead air. So they actually say that in the Veritasium video, that you can get to any speed. No, I think the argument would be is there's a certain speed you get to where you've now lost your advantage of escaping the dead air, and so you don't gain anymore. So it does have a maximum speed. So again, their math, they don't have complete and rigorous math on this subject, and they pretend they do, and they don't. But anyway, so I don't know if I want to mess with further. But yeah, it does seem sort of free energy-ish, because in a sense, if I go back to the water wheel example, there doesn't seem a limit, of the fact that you have to lose some energy to the friction with the ground, but it's a small percentage of the total energy you're getting from the water. So there is this, just make the water go faster and I can go faster, or if I go faster, I'm making the water go faster argument, where it just goes to some infinity. And I don't think it can do that. But anyway, yeah, I suppose the channel is called DraftScience, so I mean, this is sort of draft conversation, because I don't think anybody's got this nailed in terms of why it appears like it's free energy. But I guess what I'm saying is the equal and opposite reaction thing is what you're changing, and that's the friction part. So if you can take all you don't lose anything to the ground, so to speak. So in the turbine example, if I'm spinning a turbine from the water, right, the water is moving this way, and I spin the turbine. If I can eliminate how much energy has to go into binding the turbine to the ground, moving the ground, then I can apply that energy to moving in any direction. I can move with the stream, or I can move against the stream, or I can move into the stream. I can move in any direction, because once I've created the energy in some form that's directionless. So I'm really just saying that I can convert this way into exactly the opposite way, and the point would be is that as long as I don't have my wheels in the water, so as long as my wheels aren't in the water, I'm free to go this way. There's nothing impeding me converting this energy into this energy. So I'm perfectly reflecting the energy. So that's a sense, when you get rid of the friction, or you reduce the friction, you have this force. So you have a certain amount of force in a direction, and you can apply it to any direction. And you can convert its velocity by changing the mass of the thing, okay, that you're moving. So as long as your turbine weighs less than your water wheel, then you're really in business. Yeah, because then you can do the velocity. I can just change the size of the wheels that I'm rolling on the ground and make the wheels bigger. I can gain more velocity, but I might have less torque. Yeah. I mean, as long as I keep the gear ratio the same and I make the wheels bigger. It's if I make a straight axle, okay, with a big wheel here and a little wheel in the water, obviously the big wheel in one rotation is going to go a lot of distance, so I'll have a very high velocity. And it would also seem like it'd have high torque, because it's got a lot of friction because it's a bigger wheel. So I'll have to think about that part. Well, anyway, probably enough. Let's see if there's anything else subject-wise. So I don't think he said anything else in this whole pile of mush that's, all that interesting. The whole beginning of the video was some philosophical conversation about the word lucidity. It's just, it was just such jargon. Lucid. Like, that's a word that could mean again, it's just so mushy. It's like the word conscious in the first place. It just, it's not a word you can really play with because it doesn't have any really good definition. Anyway, yeah, so I'll take a pause and see if there's anything to add. I know there was something else I wanted to get to, but it doesn't appear to be happening. Yes, there was other news. Yeah, they did reinstate my Richard Feynman basic physics video, so they withdrew their copyright claim, which was very nice. And I'd say we sort of have an amicable understanding. I'm still going to do what I do. They're still going to think it might violate some element of their copyright, but it'll just be, if they have to do something, they'll do something, I guess. But whatever. But it was a learning process, and in the sense that I learned more about what they provide, which is sort of interesting. So let me get to that page. All right, so this is the California, caltech.edu, and it's feynmanlectures.caltech.edu. Anyway, and they have a lot of stuff here. They have the ones that took place in, where the hell was it? The messenger lectures from Cornell, and they're pretty good quality videos, so it's kind of nice that they have those videos as well, plus all the transcripts from the lectures, and then they have lecture notes, which really aren't too valuable. But anyway, so the basic page, the home page, the Feynman lectures, they have the book. And then they have the messenger lectures, and then they have the 117 recorded Caltech lectures, I guess they were. And then they got photos and this and that, but none of that stuff it's all interesting, but it's not, full of great info or anything. But it's all kind of good stuff. Anyway, so I just wanted to point out that, it's good. So these are tapes. They're not videos. The lectures. But again, so anyway, he handles in the actual college lectures. He handles the subject of the double slit very differently. He doesn't. I don't even know if I haven't found the one where he's doing the double slit as a college lecture. He just talks about the single slit in one place, and then diffraction gradients in another place, and kind of skips over the double slit. But anyway, I have to play more of the videos and see if there's more stuff in them and all that kind of crap. So whatever. Just pointing out that I didn't realize they had these the Cornell videos, and like I said, they're pretty good quality. Better. I think they're better than the ones that Bill Gates has, actually. But anyway, they had to buy them from the BBC. So I'm sympathetic that they had to pay the BBC for those recordings. But anyway, the world is silly. Very silly, actually. It's horribly silly. All this stuff, the copyright should have run out a long time ago on any of this stuff. It should all be public domain by now. Anyway, if we had lived in a rational world, you get 10, 20 years at the most to make your money off of something. If you can't make your money, sorry, too bad. But your rights are over. Okay, we don't pay infinite prices to a bunch of, especially, these people are all dead. It's just a bunch of greedy relatives, demanding payment for nothing, for being related to somebody. I mean, it's really just such bullshit. So anyway, no, I think that's all. I don't think there were any useful comments. So let me just check. Alright, that seems like that's all there is. So anyway, yeah. So let's see if the button works. Yeah, it did. Okay, so this has been a DraftScience video presentation. Join me next time for some more arguments made to the wind. Yeah, wind arguing. Yes, great deal of fun. So, till the next time and such.